Okay, now let's get to the technical part of the discussion of the first lecture. Here, we want to review a little bit about the fundamental or elementary functions we are going to use a lot in the discussion of the calculus. And we will start with the abstract formulation of function, and then we will discuss the property of the exponential function. Okay, so what is a function? Function just is describing the relationship between the input value and the output value. We usually use the letter x to indicate the input, and we then here use this very abstract formulation f of x to describe the output of the function relation and also its dependence on the input x. And we also could use some simpler and shorter description. Um, we can use the letter y to represent the function value. So now if you think of it, you can put this x, the input or independent variable, and the y, the function value, together as the coordinate of a point in the xy plane. So think about it. If you have all those input x for a function, and you can evaluate this f of x and assign that to the y letter, and then you can put those xy pair into the xy plane, and then you'll have the graph of function. All right, so now let's look at this specific example, which is x squared minus 1. So if we let x to be 1, the input or the independent variable, and then if you plug that into the x squared minus 1, what do we have? We have 1 squared minus 1, which is 0. So obviously 1 is the input and 0 is the output for the function x squared minus 1. And we can use perfectly this f of x to describe this relationship no matter what x value is. Okay, obviously, we can also use y equals x squared minus 1 to indicate the same thing. Okay, so along the line, if we discuss a little bit about this abstract representation of the function, so if we keep this f of x to be x squared minus 1, and what will happen if we change the input a little bit? Okay, we change the input from x itself to x plus 2. So what this notation means? This notation means we'll keep the function relationship f of x, but the input will be slightly different. It is not x anymore. Whenever you have this value for x, you have add 2 to it, and then plug into f of x. So this tells us the input for f of x plus 2 is not x anymore, it is x plus 2. Okay, and then this whole thing will be squared and then subtract 1. So obviously you can simplify this. You get x squared plus 4x plus 4 minus 1, which is x squared plus 4x plus 3. All right, similarly, what will happen if we talk about a general function, f of x plus h? So you may ask, what this h really is? So h is so-called a parameter. So if h equals 2, we get f of x plus 2. If h equals 1, we get f of x plus 1. So this is more abstract than the f of x plus 2, but the idea is about the same. So the input now is x plus h, and then we use that to put in f of x, and so the x is replaced by x plus h. So this is what we have for f of x plus h. So this is very general, all right? And we will use this a lot, especially when we try to derive the derivative. Okay, so now let's look at the familiar topic, which is exponential function. So here again, f of x tell us some sort of relationship or some sort of function definition. And here, particularly, we have this a to the power of x. Okay, so usually we ask this a to be a positive number, and a is so-called the base of the exponential function. All right, the x could be anything. And in the picture below, we have a bunch of curves that we realize for this different exponential function with different bases. And what you could see probably is for the basis that is bigger than 1, you have the curve to be increasing. But if your bases are less than 1 but bigger than 0, you can see they're decreasing. All right, so this is very interesting. And no matter what a really is, as long as they are bigger than 0, so here is exponential function, the function value is always bigger than 0. This is a feature. Okay, so now let's look at the exponential function, how we can calculate that. So to evaluate this exponential function, and we could look at the input. Remember here, this a is the base, x is the input or the independent variable. All right, so if x is n, a positive number, that means you just multiply n such bases altogether. So that's easy, right? And also another interesting point we want to raise here is that this base a could be this natural number e. Do you guys remember what the value of natural number e is? Well, I guess nobody really can because um, it is irrational number. All the decimal place will be it has an infinitely long decimal place, and you can't really just memorize all the digits. But it's about 2.7. All right, so the exponential function sometimes could be written in different form. For example, this a to the power 1/2, and we have a different way to write it. Yes, it is exactly the square root of a. So for example, if a equals 4, and 4 to the power 1/2 is just a square root of 4, which is 2. All right, so that's easy. And another thing is the exponent. If you have the exponent to be negative, that means you just divide this exponent into the denominator. So that's also very useful for the calculation of the exponential function. So here, let's use this negative exponent to actually evaluate something here. So the 2 to the power negative 2/3 is 1 over 2 to the power of 2/3. Okay, so we could actually go a little bit further from here, but let's worry about it later after we introduce the law of the exponents. And 3 to the power negative 2 is 1 over 3 to the power 2, so it's 1 over 9. And here this is 1 over 4 to the power 1/2, which is what we calculated before, which is 1 over square root of 4, which is 1 over 2. All right, so well, this is interesting. So can we rewrite this into this exponential form? Well, obviously. So what this really is? The 3 over there is just cubic root, right? So it's x squared to the power 1/3. And then this is indeed, well, we have to use the law of exponents a little bit, but I assume you know them before we even talk about that. So it's x to the power 2/3. So this is what we have. So this is exponential form, and this is a regular root, square root or cubic root form. Okay, so now there's something we really have to remember, and they're so-called the law of exponents. There are four different of them, and they are all very helpful and useful. And now I would just urge you to pause the video and stare at those four laws and to try to remember them. And after you get familiar with them, we can come to this to think about those examples. Okay, so now I assume you already get familiar with those four laws. Let's just look at what the first one really is. So 9 to the power negative 3. But I think we all notice 9 is nothing but 3 to the power of 2. 3 squared, sorry. 3 squared, right? And 3 squared equals 9. And then it has negative 3 on the shoulder. Okay. In the denominator is 3 to the power negative 8. Okay, then what? Then we can use the law now. So the numerator here requires the third item in the law above, right? So it is a 3 to the power 2 times negative 3, so it's negative 6. And then the denominator is still 3 to the power negative 8. And now we can use the second law. Is that right? Yeah, but we have to use the second law from the right hand side to the left hand side. All right, so this is 3 to the power negative 6 minus what? Minus negative 8. Okay, so this is 3 to the power negative 6 plus 8, so it is 3 to the power negative 2. Okay, so that's easy. And how about the second one? The second one, we got to first use the law 4 for law number 4 first. So 6 to the power 4 times y to the power 3 and then power 4. So here we have to use the law number 3, which is y to the power 3 times 4, which is 12. Okay, and then in the denominator we have 2 times y to the power 5. Okay, so first of all, we can separate this because it's multiplication in both the numerator and the denominator. Well, by the way, this 4 is on the shoulder. Okay, so y to the power 12 divided by y to the power 5. We got to use the law number 2 again. So it's the y to the power 12 minus 5. So this is y to the power 7. Well, now we have the last one, which turns out to be the most easy one, right? So we got to use the law number 3 directly, which is 3 to the power 2 times 3, which is 3 to the power 6. Okay, so those are things you have to be familiar with, and in the homework and quiz, we will use those a lot. All right. So if you're not really familiar with them, you got to practice and review a little bit, maybe read the textbook. Okay, so here we want to point out the most important exponential function is indeed the exponential function with the base to be the natural number e, and we call this the so-called natural exponential function. And this e is irrational number, is constant. And there is indeed a way for us to define this e, but we're not going to discuss in detail here. And what we really want to say about this natural exponential function is the slope of f of x equals e to the x at x equals 0. Remember, all those exponential functions are intersecting each other at the point x equals 0, y equals 1, right? So at x equals 0, y equals 1, the slope of the natural exponential function is constant 1. So that is the most important property of the exponential function that we want to have here. And we will stop this part of the video for now.